Good day everyone, my name is Rania Znaki and today I'll be presenting my work on artificial intelligence for spectrum allocation in cognitive radio networks, which is a survey. The goal of this talk is to explain how AI can optimize the way wireless networks share spectrum, a key challenge in the era of 5G and beyond. Let me start by outlining the structure of my work. First, I'll introduce the problem of spectrum allocation and why it's becoming more complex. Then, I'll discuss traditional methods and their limitations. After that, we'll see how cognitive radio and AI techniques, particularly reinforcement learning, deeper reinforcement learning, and federated learning, address these challenges. Finally, I'll present the main challenges that remain and end with key takeaways. We are witnessing an unprecedented growth in wireless communications. With billions of connected devices, the demand for spectrum keeps increasing. Traditionally, spectrum access had been fixed and licensed, meaning specific frequency bands are assigned permanently to operators or services. However, studies show that many of these licensed bands remain underutilized at certain times or locations, while others are congested. This inefficient usage of radio spectrum highlights the need for more dynamic and intelligent spectrum management. The concept of cognitive radios had proposed to address this issue by allowing devices to sense and use temporarily available spectrum holes. Before any real adoption of AI, researchers used optimization algorithms such as genetic algorithm (GA) and particle swarm optimization (PSO). While these methods can find near optimal solutions, they struggle to adapt rapidly to changing environments in real time. Other approaches include game theory, which models user interaction to ensure fairness, and heuristic methods like ant colony optimization and bipartite matching. These methods improve distribution compared to static allocation, but they still face major difficulties in guaranteeing quality of service, especially for secondary users. Overall, they lack the speed, adaptability, and learning capability needed in modern dynamic networks. Cognitive radio, or CR, introduces intelligence in wireless communication systems. It allows unlicensed users, known as secondary users or SUs, to temporarily access underutilized license bands belonging to primary users or PUs. The core process here is dynamic spectrum access or DSA, which enables more efficient use of the spectrum. Through spectrum sensing, cognitive radios can detect unused channels, known as spectrum holes, and access them without causing interference. This technology forms the foundation of AI-driven decision-making in spectrum allocation. Now, let's see how artificial intelligence transforms this process. AI enables intelligence, adaptive, and autonomous spectrum management. Reinforcement learning, or RL, allows a radio to learn the best allocation strategy through trial and error. While using algorithms like Q-learning, the agent interacts with the environment, receives feedback in the form of rewards, and gradually learns to minimize interference while maximizing throughput. Deep reinforcement learning, or DRL, extends this to high-dimensional environments with multi-agent DRL support, multiple radio learning collaboratively, an essential feature in dense wireless networks. Finally, federated learning decentralizes model training. Instead of sending raw data to a central server, each device trains locally and shares only model updates. This approach improves privacy, scalability, and efficiency, making it ideal for distributed cognitive radio networks. Although AI has shown great promise, several challenges remain. First of all, quality of service, where spectrum availability is uncertain and changes over time. Guaranteeing consistent performance requires accurate spectrum prediction before allocation decisions are made. Regulatory compliance, Where AI-driven systems must operate within global communication standards and avoid interference with licensed services, they must also consider ethical and legal implications, such as data privacy and fairness. Energy efficiency is yet another problem. Many AI models are computationally heavy. For resource-constrained devices, this is impractical, which is why new approaches like TinyML aims to create lightweight, energy-efficient models that can run on edge devices. Addressing these challenges is key for real-world deployment. To conclude, artificial intelligence has fundamentally changed how we approach spectrum allocation. It brings adaptability, scalability, and efficiency, enabling networks to make intelligent decisions in real time. Reinforcement learning, deep learning, and federated learning together provide a powerful toolkit for achieving dynamic and efficient spectrum access. However, challenges such as security, energy efficiency, and regulatory compliance must still be addressed before large-scale implementation becomes practical. Thank you for attending. If you have any questions, please reach out to me to rania.zaki@uca.ac.com. Merci.